Hi everyone, I'm Xiaohui. I'm from AI Earth team in Alibaba DAMO Academy. Today, I'm very glad to introduce this AI-enabled radar nowcasting to everyone. And the weather forecast usually can be divided into different types according to different time horizons, from nowcasting to short-term weather forecast, extended range weather forecast, seasonal forecast, decadal weather forecast, and climate weather forecast. As the forecast horizon increases, the forecast confidence also becomes lower. And today we will focus on the nowcasting, which largely used dependent on the AI models to forecast the future 0 to 6 hours rainfall. The other types of weather forecasts usually use the physics-based numerical weather prediction models. Besides the nowcasting, the artificial intelligence model can also be applied into other domains of weather and climate prediction. Like in our renewable energy forecast, the AI model can usually help us to correct the numerical weather predicted wind and solar power, so to predict the future amount of solar and wind power that's going to be generated in the next day. Also, the AI model can be applied to post-process the NWP model outputs to make it more accurate. And it can also help to classify different weather phenomena based on the satellite images. In this slide, it shows a paper published in 2019 on Nature that tells us how AI can beat the state-of-the-art physics model in terms of answer forecast. On the plot, the red line shows the deep learning model forecast. It uses a simple CNN model. And all the other lines are physics-based model. The plot shows that physics-based model, the correlation scale drops below 0.5 after 12 months. And the CNN model is able to forecast higher than 0.5 correlation scale up to 18 months. So it shows the potential of AI model in beating the physics model in the answer forecast. The ECMWF, the European Center for Medium Range Weather Forecast, is the world's leading weather forecast center. And in their roadmap for the next 10 years, they already put a lot of emphasis on the importance of AI. Showing on this slide, it shows that the AI will play a very important role in the whole workflow of the weather forecast generation, from the observations, like the observation data cleaning, to data assimilation, and to various physics components in the numerical forecast model and the data post-processing. So in the entire workflow of the forecast generation, the AI will play its part. And today, as our focus is on the radar nowcasting, I will first briefly introduce what is radar nowcasting. Radar nowcasting is trying to use the historical radar reflectivity of past n hours to forecast the future m hours with radar reflectivity. And traditionally, people use optic flow method. This method is trying to predict the future movement of clouds, but it cannot predict the cloud formation, development, and dissipation. Therefore, its performance after 1 hour is going to be very bad. So we mentioned radar reflectivity, but what is radar reflectivity? It is the amount of transmitted power returned to the radar receiver and can be used to detect precipitation, evaluate storm structure, and determine hail potential. The table on the right shows the strong correlation between the radar reflectivity and the rainfall rate. So the higher values of radar reflectivity usually indicates the higher amount of rainfall. The plot on the left shows the spatial coverage of China's new generation radar network. So besides the radar reflectivity, there is a new type of radar called polarimetric radar. It provides more information than just radar reflectivity, such as differential reflectivity, specific differential phase. These two variables can tell us the microphysics information about the clouds or the droplets. So but it remains an issue or question about how can we fully use of this extra information to improve the to improve the nowcasting. This figure shows the history of development of AI models that used in radar nowcasting. In 2015, Shi et al. Proposed the ColorfulClouds. It was a very innovative idea to treat the rainfall forecast problem as the spatial and temporal sequence problem. The ColorfulClouds model can effectively make use of the historical information to forecast the future sequence. And in 2017, that Wang et al. They proposed PredRNN, and they introduced the spatial temporal memory to improve upon the ColorfulClouds. Until 2020, the Google research they proposed MetNet. They include multiple data sources, including radar and satellite images, longitude and latitude, and time information, and they claim their forecast can be up to 8 hours. AI-Earth used a different nowcasting model structure than previously mentioned. We used the U2Net model. Why we are not using the previously mentioned model is because we are doing the nowcast for the entire China. And the previously mentioned model is not able to process such big image covering the whole China. And this is an animation shows our AI-Earth radar nowcasting platform. And you guys are welcome to visit our website to check out if our forecast is accurate or not. We did our own evaluation, and our results shows that our forecast is better than the optical flow method, especially when the reflectivity is higher than 35 dBz. And in the development of the radar nowcast system, we found there are some issues. For example, the visualization issues. Previously, our forecast results is very ambiguous, as the plots in the middle shows. It's different from the ground truth or the actual radar reflectivity. So we use GNN to learn the radar reflectivity images to produce a more realistic radar reflectivity forecast. Also, we add Himalaya 8 satellite data because we think the Himalaya 8 satellite data has multiple channels that can measure different physical properties of the atmosphere and can provide some extra information than radar reflectivity. So we select some channels and did some experiments, and it shows accuracy improvement by adding the satellite data. We also include the numerical weather prediction data to push our nowcast from 0 to 6 hours to 0 to 3 hours to 0 to 6 hours. We select U and V wind component, specific humidity, and surface pressure from the numerical weather prediction model data. And after doing that, our 6-hour forecast is as accurate as our 3-hour forecast that we have previously. As radar reflectivity is not the end product of our nowcasting system. In reality, people care more about precipitation or rainfall. So there is one last step to convert the radar reflectivity to precipitation. A traditional dynamic ZR relationship method needs to calculate the coefficient A and B to convert the radar reflectivity to the rainfall amount. And we compared the two methods. One is end-to-end method that use the historical radar reflectivity to forecast the future rainfall directly, or use two-stage method to first forecast the future radar reflectivity, then based on the radar reflectivity to forecast the future precipitation. Our comparison shows that our end-to-end method is better than the two-stage method and better than the dynamic ZR relationship method. And that's all for today's presentation. Thank you.
Hello everyone, welcome to this webinar on intelligent weather forecasts for better life. First, I'd like to show my thanks to Alibaba Cloud for organizing this webinar. I'm Tianmeng, leader of Weather Forecast Algorithm Group in ColorfulClouds technology. My research focuses on deep learning for weather forecasts. I'm excited to share my thoughts on intelligent weather forecasts and to briefly introduce air quality forecast here. Before getting to the main topic, I'd like to give you a short introduction to the company I work for, ColorfulClouds Technology. Founded in 2014, it always aims at improving our lives with AI. Our ColorfulClouds weather app was released in 2014 to provide weather forecasts for people, especially precipitation nowcasting and air quality forecasting. My sharing today contains four main parts. Firstly, I'm going to talk about how we could make innovations in weather forecasting, especially with the help of deep learning. Then I will introduce the background of air quality forecasting and show how we use graph neural network and GRU to model PM2.5 forecasting. Where could innovations in weather forecast come from? This slide shows the weather forecast process from collecting observations to meeting users' demands. There are a variety of observations, such as data from weather stations, balloons, radars, satellites, and so on. These data are fed into various models to generate many meteorological products, including temperature, wind, precipitation forecasting, alerts, and real analysis data, which help users in making decisions and do good to our society. We can try to innovate in each stage of the whole process. Roughly, I think innovations in weather forecasting can be classified into two kinds. One is to improve the accuracy of weather forecasting by developing new models or taking more observations as input. The other kind is that we combine weather data and industrial data to provide customized weather forecasting, which is able to save costs and improve efficiency for industrials. Here is a list of interesting problems suitable for deep learning, such as air quality forecasting, weather nowcasting, post-processing of numerical weather prediction, reanalysis of historical data. It is noteworthy that WeatherBench is a dataset based on ERA5 reanalysis data. It is an attempt to make long-term weather forecasts comparable to numerical weather predictions in a data-driven way. Although deep learning is promising in improved weather forecasts, a number of challenges remain. In some situations, there is still a lack of observation data for training deep learning models. Extreme weather events are vital but hard to predict. Since our system is complex and dynamic, we have to incorporate domain knowledge to guide deep learning. Also, it's difficult to deal with various types of meteorological data. In the second part, I'm going to take air quality forecasts as an example to show how we use deep learning. Let's get started with background of air quality forecast. There are several air pollutants in everyday life, but for simplicity, we only take PM2.5 concentration into consideration. What is PM2.5? It refers to tiny particles with diameters smaller than 2.5 microns, and it is very harmful to human health. Visibility suffers when PM2.5 concentration is high, as shown in the picture. PM2.5 particles are suspended in the air, so their transportation and diffusion are tightly related to weather condition. When weather condition is stable, those particles are hard to diffuse, then accumulate instead. But they can be transported by wind from one place to another, as shown in this demo. Air pollutants flow eastward, and at the same time, the wind blows from west to east. Besides the wind, there are other key factors of PM2.5 forecasting, including humidity, precipitation, and planetary boundary layer height. Humidity promotes the generation of PM2.5 particles, while precipitation helps clear those particles. Additionally, PM2.5 concentration is inversely related to PBR height. Now, we are familiar with the relation between PM2.5 and weather condition. I'm going to talk about how we model PM2.5 forecasting by graph neural network and the GRU. What kinds of data do we have? PM2.5 concentrations from air monitoring stations and numerical weather forecast data. The motion of PM2.5 is also a dynamic process, so we need to deal with spatial temporal dependency. Let's have a look at the stations in the image. They are unevenly distributed, which makes it difficult to handle spatial relation for CNN. Therefore, it is a good option to build a graph with cities as nodes and transport passes as edges. Meteorological attributes of nodes and edges are shown in Table 1 and Table 2. We take the average as PM2.5 concentration of cities. In graph neural network, it's convenient to consider transportation of PM2.5 from one city to another by aggregating neighbor nodes information through edges. In order to capture short-term and long-term interactions of a city, we use GRU. In this framework, X denotes PM2.5 concentration and PQ and G denote graph information. At time t, we take PM2.5 concentration and graph representation as input to predict PM2.5 concentration at the next step. Putting GNN and GRU together, we arrive at PM2.5 GNN. Let's go through the algorithm details. First of all, we have as input observed PM2.5 concentration X, node features P, edge features Q, and adjacent matrix G. The target is to predict PM2.5 concentration in 72 hours. At time t, for every node, we take node features, neighbor node features, corresponding edge features as input of GNN to obtain aggregate information through edges. Then, node features and aggregated information are processed by GRU to predict the hidden state of every node, with which PM2.5 concentration at time t is derived by MLP. Things like this go on recurrently until we get all predictions. Parameters of GNN, GRU, MLP are shared across all nodes. The correspondence between PM2.5 dynamic process and PM2.5 GNN are illustrated below. In a nutshell, spatial relations are encoded by GNN and the temporal relation as well aggregated information are processed by GRU. We train our models on a 4-year dataset, and the task is to make PM2.5 forecasting in 72 hours. Let's have a look at the results of different models. GRU performs worst since it ignores interactions between nodes. PM2.5 GNN performs better than GCLSTM because the influence of wind is implicitly contained in edge construction. Also, the ablation study shows that there is a significant drop in performance for models without PBR height. This slide shows a case study of dataset 3. forecasting series of PM 2.5 is better matched to ground truth for PM 2.5 GNN. Our work was published as a post paper in 6th Visual 2020, and you can read our paper and codes for more details if you are interested. That's all. Thank you for your attention.
For the rainfall forecast, actually nowcast should be the most accurate. But nowcast has the issue that can only provide the valid rainfall forecast up to 6 hours. There might not be enough time for people to react. So we still need to rely on the physics-based numerical weather prediction model, which can provide us a 1 day ahead forecast. The physics-based model may not be as accurate as the nowcast. So we need to combine them together to make the warning. And also, the AI model can help to correct the biases in the model forecast. There's also another technology used in the numerical weather prediction model called ensemble forecast. Ensemble forecast is basically trying to let the NWP model start with slightly different initial conditions, as we know that the true state of the atmosphere is never known. So our initial conditions is never going to be 100% accurate. But initial conditions has very large impact on the future forecast. That's why we need an ensemble. An ensemble can help us to give us the probability of the future event. And we can try to use the AI to give us better probability based on the ensemble model outputs. Yeah, that's my answer.
Intelligent weather forecasting can definitely improve effectiveness of precipitation warning, especially of short-term warning. Actually, long-term warning still relies on traditional numerical weather prediction. In the case of Zhengzhou torrential rains last month, alerts were issued in advance thanks to numerical weather forecasting. But it's still very difficult to provide warnings for extreme precipitation events hours in advance. Because the Earth system is so complex that weather system in nature possesses chaotic behaviors. Fortunately, real-time observations from radars and satellites make it possible to detect extreme precipitation events. Whether or not to issue precipitation alerts is usually determined by data of historical accumulated precipitation and the precipitation forecasting of the following hours. Once total precipitation exceeds the given threshold, warnings will be sent. The data of historical accumulated precipitation can be obtained from weather stations, and AI-based radar nowcasting can be used to estimate precipitation in the following hours. So with the help of AI, we can send warnings effectively within 2 hours. The technology behind is the close correlation between radar echoes and the precipitation. And the radar nowcasting can be achieved by training deep learning models against tons of radar images.
So besides the weather app, there are also many other applications, such as in the renewable power forecast, that AI can help to make the forecast of the future solar and wind power generation. And also for the aviation industry, they need the weather forecast so that the airplane can take off and landing safely. Because if there is a strong convective system, it's not safe for the airplane to take off or land. Also for the utility company, that they need the weather forecast as there might be lightning strike on the transmission lines, or there could be typhoon, or there could be some other weather, extreme weather that causes the transmission line broken and cause the blackout. And they can determine which area that could have this potential blackout. They can send people ahead of time to fix the transmission line faster. Yeah, and also the insurance company might also need the weather forecast too, so that they can tell their customer where there could be flash floods, that they can avoid going to that area and to reduce their loss.
Intelligent weather forecasting has a broad impact on many areas, such as transportation, agriculture, airline, and disaster prevention. On highways, precipitation nowcasting can remind drivers to be cautious to heavy rains and wet roads. Moreover, precipitation nowcasting helps car-sharing companies estimate user demands and better redistribute cars to provide services for more users. For pilots, they often refer to radar nowcasting to decide if the weather is good enough for taking off or landing. In agriculture, detailed and accurate weather forecasts can help farmers to make the right decisions, such as whether, when, and how much to irrigate. In disaster prevention, the accumulated precipitation data and the precipitation nowcasting can guide the government to alert people or evacuate people in time. Because precipitation nowcasting updates very frequently, it's very helpful for people who are in danger.
So AI the leading AI technology can also be used in the development of the numeric weather prediction model. So there are some researchers that they're trying to replace some physics components in the NWP model, such as a radiation scheme, planetary boundary scheme. Because the radiation scheme runs very slowly, and some researchers trying to replace the radiation scheme with a neural network. And the neural network plus the GPU can accelerate the radiation calculation to reduce the amount of time of running NWP model. Also, there are people that are trying to use the AI model to do the satellite data retrieval. So use the AI to process the satellite images to learn some physical properties of atmosphere, like the humidity, temperature, or clouds from the satellite data.
Yes, for sure. Some of the technologies have been rather popular. Take ColorfulClouds, which I know best, as an example. With more than 5 million monthly active users, we offer every user minute-to-minute, kilometer-to-kilometer precipitation nowcasting in 2 hours, and our accuracy is over 80%. Our rain notification often prevents users from rain. If you know about weather forecasting, you may understand that it is an incredible achievement, and this achievement comes from our constant efforts on radar denoising and radar nowcasting.
AI models, especially deep learning models, are very powerful when there are enormous amount of data. And in the domain of meteorology, we have tremendous amount of data, satellite data, and I think we can try to reconstruct the three-dimensional wind and thermodynamic structure of the atmosphere by using satellite data and the deep learning models. And we can use the measurements from weather balloons, LiDAR, and wind profiler, which measures the vertical profile of the atmosphere. As for many weather forecasting problems, one critical challenge is we don't know the true state of atmosphere. So I think it's going to be very meaningful if we can try our best to get the three-dimensional structure of the atmosphere. And that's the first one. I think the second one is for the sub-seasonal to seasonal forecast. As the forecast is related to the somewhere far away, and the physics-based model may not be very good at predicting to do the sub-seasonal to seasonal forecast, as the forecast uncertainties grow with time. And we have already seen that the AI model can beat the physics-based model in ENSO forecast. I think for other sub-seasonal to seasonal forecasts, we can try to use deep learning model and to see if we can achieve better results than physics-based model.
There are many valuable things that we need to work on. Recently, extreme weather events have caused tremendous economic costs and claimed lives. How to make full use of weather forecasting to reduce loss and save lives becomes more and more important. It's valuable to provide more refined weather warnings to people, which requires us to make finer forecasts both spatially and temporally. Besides weather nowcasting, AI-based long-term weather forecasting will attract increasing attention in the future. As far as I see, effective combination of deep learning and numerical methods is more likely to further improve long-term weather prediction. In addition, weather forecasting and solar radiation forecasting are significant for wind power stations and solar power stations to predict how much electricity will be generated. A slight improvement in forecast accuracy would lead to huge economic values, and it is likely to be achieved by combining multiple observations and numerical weather forecasting data in deep learning.